Say we have the following functions, which are the composite of two or more separate functions, where a composite function is simply just a function with one or more separate functions inside another. Take for example our first function, which is a composite p of q of x, where p of x is sine x and q of x inside it is 3x. Or our fourth function, which is a composite p of q of r of s of x, where p of x is x squared, then q of x inside it is tangent x, then r of x inside q of x is secant x, and lastly, s of x inside r of x is 2x or 1 plus x squared, giving our final result of tangent squared of secant of 2x over 1 plus x squared. And we are asked to find the derivative of these. Well, we clearly can't find the derivative of these by using any combination of basic derivative theorems, the product rule, or even a quotient rule. So we have to devise a new rule. And the rule we devise is called the chain rule. And in this video, which will be part 1 of a 2-part series, I will go over the derivation of this rule. So given a function, f of x equal to p of q of x, a composite of two separate functions, p of x and q of x, we want to derive the derivative of this function. Or in other words, we want to prove the chain rule. So we write down our derivative. And first, I'm going to let q of x be defined by another variable u. And by doing so, our composite simplifies to a single function, p of u. Now you're probably like, wow, was it that easy? Now I can just solve the derivative, because now I just have the derivative of p with respect to x. Indeed, we do, but notice that the independent variable for our function p is not x, it is instead u. So differentiating with respect to x wouldn't mean anything. The u would be just treated as a constant. To understand my point, take for example this. F of v equal to 3 times v squared plus 5v minus 6. If you were asked to differentiate this with respect to x, it would all be 0, right? Because v would be treated as a constant. However, if you were instead asked to differentiate this with respect to v, then it's obvious that you would get something else, the derivative of p, but as a function of v instead of x. In fact, anytime you take a function of a certain variable and differentiate it with respect to that same variable, be it x, a, or even omega, the answer is always the derivative as a function of that variable. Otherwise, you always get 0. So with that fact in mind, what we want to do is that the derivative p of u be taken with respect to u instead of x. Or in other words, we want to replace the du with the dx. Well, where do we get a du from? Simple. We just times du over du and then switch the dx and du on the bottom. Okay, good. We have one problem solved. Great. But by doing so, didn't we create another one? What about the du over dx on the outside? Wouldn't that get us 0 every time if we were to evaluate it? Not quite. Because just like when you are asked to evaluate dy dx and y as a function of x, u here is a function of x also, as in q of x, giving du dx a derivative of q as a function of x. So we plug this derivative of q of x for du dx back in along with q of x for u everywhere else and get this. Now, even though the first derivative looks a little complicated, as we have dq of x on the bottom, all that matters is as long as we have q of x in our function p and next to d as our bottom differential, as mentioned earlier, we know that this expression then means the derivative of p as a function of q of x. So with this in mind, we can simplify and safely rewrite in prime notation. And we finally have our chain rule, which states that to find the derivative of the composite of two functions, p of q of x, all we do is take the derivative of the outer function p prime and leave this derivative as a function of the inner function q of x, meaning treat q of x as an independent variable and plug into p prime, and then multiply the derivative of the inner function q prime x on the outside. Now that we have proved this rule, you're probably like, well, this rule only takes into account a function that is a composite of two functions. Well, what about a function that is a composite of more than two functions, as shown in the beginning of this video? Well, in that case, then you just take the chain rule on top of the chain rule. To understand what I mean here, take for example a composite of three functions, p of q of r of x. To find the derivative, the procedure for this is to let the inner composite q of r of x be equal to another function z of x, reducing the total composite down to 2, p of z of x. And now that we have a composite of 2, we can apply the chain rule and then get the following: p prime of z of x times z prime of x on the outside. We will then plug our inner composite q of r of x in for z of x and then get this. Notice how we now have the derivative of our inner composite, the quantity q of r of x prime on the outside, requiring a second chain rule to break it down even further. So we apply that chain rule and then get this: p prime of q of r of x times q prime of r of x times r prime. And that's exactly what I meant by a chain rule on top of a chain rule, because that's exactly what we did. We had our first chain rule of p of z of x, then we had our second chain rule of q of r of x. Similarly, if we had a composite of 4 functions, we would then require 3 chain rules, one on top of another and on top of another, and so on, n minus 1 chain rules for n composites. Hence where the name comes from, chain, because taking the derivative creates a chain of other derivatives multiplied to it. Hopefully that makes sense. So there you have it, the derivation for the chain rule. For practice on applying this rule, stay tuned for part 2 where I will go over examples. Until next time, thanks for watching.